Our language is filled with metaphors. It's been argued that this is because human thinking is at its core metaphorical. We draw analogies from more familiar concrete domains to more unfamiliar abstract ones. And when new technologies appear, we tend to describe them in metaphorical terms. And you've probably noticed that we are really grasping for metaphors that we can use to not only talk about large language models, but also to help understand them. So what I'd like to do is to go through some of the metaphors that I've seen people use when discussing large language models and reflect on which of these I think are on the wrong track and which are, if not right, at least useful. The first metaphor draws an analogy between large language models and databases. When OpenAI showcased ChatGPT's and later GPT-4's performance on various standardized tests, one type of response was that a claim that GPT passed the bar exam or got a certain grade on AP art history was like saying that Google or Wikipedia passed an exam. Let's unpack this. If you wanted to see how well Google does on some question, well, for a simple lookup type question, like what's the capital of Botswana or how many cups are in a pint, you'll get a straightforward answer, especially now that Google introduced those info boxes to keep you on the search page rather than go hunting for the answer in the links. For more complex questions of the sort found on standardized tests, though, Google might provide some relevant bits of information, but then you, the test taker, would need to figure out how to use it to answer the question. Assuming the exact question isn't just available online next to the answer, databases require that you figure out how to make the information you retrieved relevant to the specific question you're answering. If the question asks you to rank the options from most to least important, for example, you'll need to use the information you found in your search to do that. A language model is like Wikipedia or Google in the sense that a prompt leads to an output, just as a search engine query leads to a set of results. But the similarity kind of ends there. A language model is attempting to interpret your question rather than just use it as a lookup string. When you pose a question to a large language model like ChatGPT, you get an answer. It might not be correct, but it's still an answer. And it's the model, not you, the test taker, that is figuring out both which information in its training set is most relevant to the question and how to use it to answer the question. This fundamentally breaks the analogy between what happens when you pose a question to a large language model and when you search a static repository for information. Now, however skeptical one might be in granting these models anything we might want to call thinking or reasoning, a few minutes of interacting with them is enough to see that what they're doing is very little like database lookup or traditional search. For example, shortly after ChatGPT was released, Steve Piantadosi asked it to generate a dialogue between pasta and udon, where pasta only speaks in microaggressions. What it produced is probably not as good as what a professional comedy writer could produce, but it's a whole lot better than what I could have done. No database, no matter how large, can do that. The metaphor of language models as databases fails. The next metaphorical frame is large language models as mimics. Back in April, the New York Times featured an interactive demo as part of its Upshot data-focused column called Watch an AI Learn to Write by Reading Nothing But Jane Austen. The author, Adish Bhatia, wrote, "While the inner workings of these algorithms are notoriously opaque, the basic idea behind them is surprisingly simple. They are trained by going through mountains of internet text, repeatedly guessing the next few letters, and then grading themselves against the real thing." This is a really nice summary of what they do. Large language models like ChatGPT are autoregressive, meaning that they attempt to predict the present using evidence from the past, and they're self-supervised, meaning that the error that guides their learning comes from the training data itself, rather than from an external teacher, as is the case for supervised models. Now, there is some supervised learning that's added later, and it makes these models much more usable, which is very interesting in itself. We'll put that aside. So the model tries to predict the next bit of text. It then gets to actually see the next bit of text, adjust the weights so that the prediction better prediction error is lower, and it keeps going, lowering the prediction error bit by bit. What the New York Times did was train a baby language model on just the works of Jane Austen or Shakespeare, Star Trek scripts, or Harry Potter, and they had it generate text after each bit of training to show what it can do at that point. And first, it's just generating gibberish. Then word-like units start to emerge. It's not mixing letters, punctuation, and numbers anymore. Then words, first small, more frequent words, then bigger, less frequent words, then larger and progressively more grammatical phrases. It's still largely nonsense. It's a baby model after all, but you get to feel the style of Jane Austen or Shakespeare or Star Trek, not because it's repeating their exact phrases, although it does that too, but because it's generating text that's similar. And so, Bhatia concludes, language models are a kind of universal mimic. They imitate whatever they've been trained on. With enough data and rounds of training, this imitation can become fairly uncanny, as ChatGPT and its peers have shown us. In the months after ChatGPT came out, it was common to see references to autocomplete. People were being asked to think of language models as being like autocomplete on their phones, but bigger, glorified autocomplete. A more sophisticated version of this metaphor is Emily Bender and colleagues' claim that these models are, quote, stochastic parrots. An implication is that the language produced by large language models is as meaningless as a parrot's mimicry of speech. If we find it meaningful, it's because we as people can understand language. Just like if we understand a parrot's mimicked speech, it's because we understand it, not because the parrot does. Bender and colleagues argued that any real understanding was in principle not possible for models trained only on language, because all such models have access to is the relationship between one bit of language and another. They don't have access to the real world, and without this grounding in the world, there cannot be any real meaning. Now, if the abilities of large language models ended there, if all they could do was imitate prose from authors they've been trained on, I wouldn't be here talking about this stuff. It's precisely because the abilities of these models, that they go so far beyond mimicry that people are freaking out. After calling language models universal mimics, Bhatia goes on to talk about how when you train these models using this very simple learning rule on corpora millions of times larger than the works of Jane Austen, all sorts of new abilities begin to emerge. The models can answer novel questions, make connections between very different domains of knowledge, and on and on. Well, this doesn't sound very much like mimicry anymore. And as we'll see, these abilities call for an entirely different way of thinking about large language models. We need a different metaphorical frame. Okay, so number 1, database. Number 2, mimic. We're up to number 3, language models as compression. The most vivid form of this metaphorical framing comes from the writer Ted Chiang's New Yorker essay called ChatGPT is a Blurry JPEG of the Web. Chiang is worshipped by many of the people who are most vocal about these models, and so it's not a surprise that the essay got a lot of attention in the machine learning community. If all you've done is read Chiang's stories, I encourage you also to actually listen to him speak on the subject of AI. There's a really remarkable interview that Ezra Klein did with him back in 2021. Anyway, perhaps because so many in the machine learning community love Chiang's writing, the response to his article was uncharacteristically reserved. People disagreed, but I didn't see anyone calling him an idiot. I got the sense that folks didn't want to come across as disrespectful being fans of his novel. When you compress an image using a lossy format like JPEG, you're replacing sections of the image with simpler versions. So a patch of dappled blue sky might be replaced by a patch of more constant blue. The resulting file is smaller, but some fine details are irretrievably lost. The compression metaphor helps explain why language models struggle with factuality. It's precisely because they're not mere databases or mimics that they struggle with giving you back a simple fact, even if it was part of their training. They can't help but fill in, approximate. And it's this approximation that gives them their flexibility, it also is what produces behaviors that people have started to call hallucinations. Many of us in psychology and cognitive science recognize as confabulation. That's the more correct term, but I don't want to be overly pedantic. Okay, so it's valuable to emphasize this lossy side of compression. But what the essay missed is that a good compressor learns a model of the world. To be able to replace one thing with a simpler thing that's nearly as good, one needs to learn what the things are. So, for example, a text file is much smaller than an image of the text file. That's because in a text file, the information is represented as text. Each letter is a chunk, a code, a unique code. An image of the text represents letters as a collection of pixels. The text form is a compression of the image, but if all you have is the text, you have no idea how it's arranged, what the font is, what the size is, and so on. So a JPEG compressor is not very smart. It has no idea what a sky is, or that the sky is more likely to be at the top of an image than the bottom. It doesn't know what a face or a person looks like. All it's doing is looking for repeated patterns of pixels and replacing them with slightly simpler patterns. Even so, it can reduce the size of an image by a factor of 10 with really minimal perceived loss of quality. Now compare this to a smarter compressor. Let's take as an example a generative model like Stable Diffusion. This has been trained on about 4 billion images, at least as of half a year ago or so, and as well as the accompanying captions or nearby text. Now, you can download this model to your machine, and what's remarkable is that the full model, all that it's learned, is about 4 gigabytes. So 4 billion images have been compressed into 4 billion bytes. I don't know what the average size of the training images is or what resolution they're at. Let's say it's 50K. Well, that's a 50,000 to 1 compression ratio. Remember, the JPEG was 10 to 1. Now, if we try to recover any of the original images, we can't, at least not very well. We get approximations. Even the Mona Lisa isn't really right. She has too many fingers, and colors are kind of wrong. It's still, though, unmistakably the Mona Lisa. Stable Diffusion has learned a whole lot about the underlying units of our visual world and how to combine them in reasonable ways. That's what a smart compressor can do. Ask it for a piranha made of lollipops riding a unicycle, and you get a piranha made of lollipops riding a unicycle. So yes, it's a kind of compressor, but if you're going to get really good at compressing, you've got to start learning larger and larger units, how to combine them. You have to know something about what a face looks like, which parts vary, and how, about the differences between riding on a unicycle, in a car, on a horse. Now, this connection between compression and learning a model is not new. It's the basis, for example, of the principle of minimum description length. What's true of these image models is also true of language models. When we learn an effective compression scheme, we're learning something that allows us to do much more than make a blurry JPEG of the web. Finally, we come to the two metaphorical frames that I think capture the essence of large language models better than the three I've talked about so far. They might be wrong, but I think they're useful. I'll talk about them together because they are, in a sense, two sides of the same coin. So we have large language models as simulators, and the other side, large language models as general pattern machines. The most provocative explication of this idea of large language models as simulators comes from a really long blog post by the user Janus. That's the Roman two-faced god of beginnings and transitions. So we have a two-sided metaphor and a two-faced god. Now, the full post talks a lot about artificial general intelligence, an idea that I personally find to be based on a rather faulty understanding of human intelligence, but never mind that. The basic idea is that in the service of lowering next token prediction error on a large enough data set, the language models end up finding larger patterns that can be used to instantiate simulations. These include simulations of the physical world and also simulations of different kinds of agents. That's how we get the weirdness of having ChatGPT answer a plumbing question correctly when asked to answer as an experienced plumber, but not when it's answering as a computer scientist. The different prompts result in instantiating somewhat different simulations. When I've talked to people about this aspect of language models, that in the service of lowering error, they can learn a whole lot about the structure of the world, the response I often get is, well, sure, but how often do we talk about this stuff? How is this possible? I think the error people are making here is assuming that these models are learning from linguistic propositions. So, okay, sure, they can learn that the sky is blue because we say stuff like blue sky, but we don't talk about what objects can balance on what objects. So how in the world can they know how to stack various objects on top of one another in a stable way? So what's happening here is people are kind of confusing the learning algorithm, next token prediction, with the information that can be learned by running this algorithm. Yes, it's most likely true that we don't talk about how to stack various objects. So how can a model whose only access to the world is through language used by people learn this kind of information? The way to think about it is that the way we use language is multiply constrained by the world. And so one way, perhaps the only way, of getting really good at predicting the next token across very many different contexts is to figure out what the world is actually like, or at least actually like to the people producing the language on which it's trained. Now, it's worth pointing out that brains are simulators in many of the same ways. They also learn by a whole lot of prediction. We get to directly experience some of these simulations in our imagery, in our imagination, maybe most compellingly in our dreams. In our normal waking consciousness, we often feel like we are in direct contact with the world, but of course this is largely an illusion. Our contact is mediated by models. Traditionally, we cognitive scientists think of these models as being learned through our senses. When it comes to learning from language, we tend to think, again, about propositional information, like, I don't know, that Germany invaded Poland in 1939. Well, sure, it's difficult to imagine learning history in the absence of linguistic input, but as large language models show, language can be used to learn a whole lot more. And that's because the learning is not limited to encountering statements about specific facts. The information is in the connections among the words. It's in the distribution of words. Learning to predict well seems to involve learning some of the overarching regularities that give rise to these distributions. Recently, there's been a spate of papers discussing the phenomenon of grokking in transformer models like GPT. Grokking, as an aside, is a word invented by Robert Heinlein in his book Stranger in the Strange Land to convey the idea of a deep, empathic kind of understanding. That was in 1961. And in the next few decades, computer scientists adopted the term to differentiate merely knowing how to code in a language from grokking the language, meaning you've sort of internalized its logic and abstractions. You really deeply understand it. Okay, so what does this have to do with language models? So ordinarily, the more a neural net is trained on a particular training set, the more it's likely to overfit, to essentially memorize the training set, especially if it's a large model with the ability to just memorize the set and lower its prediction error that way. And so you can see that overfitting by an increase, at some point, an increase in the error on validation sets. So the interesting thing that's been observed in these larger transformer models is that there are cases where continued training beyond the point of what looks like overfitting sometimes results in these sudden and drastic drops in the error on the validation sets. The model is said to grok the phenomenon. It suddenly, quote, understands the deeper underlying principle. And this gets us to the other side of large language models as simulators. And this frame is right in the title of a recently published preprint by Suvir Mirchandani, Large Language Models as General Pattern Machines. The authors of this preprint test several models on their ability to complete abstract sequences represented using arbitrary notations. For example, they were given examples of Francois Chollet's abstract reasoning corpus. They had to complete functions like a sinusoid that's decreasing in amplitude, again, using completely arbitrary text notation. These are not vision models. To control a robotic arm, tasked with rearranging objects in just a text world, and to learn to keep a stick vertically oriented by moving a point left to right. So imagine balancing a pencil on your finger. And remarkably, the models are able to do this reasonably well, to do all of these tasks using only in-context learning after having been trained just on language. So training on language has given these models the needed machinery to learn this range of behaviors on which it had no prior experience. And the authors argue that this is evidence the models have learned to detect arbitrary patterns. They are more or less general pattern machines. Now, precisely how they're able to do this and what parts of training are most important for this ability to emerge, these are excellent questions. They're also very much answerable questions. We can answer them by running experiments on the models, and in case you're wondering, no, I don't condone simply asking them how they do it. This is also why we run behavioral experiments with people rather than just talking to them. So there we have it. We have 5 metaphorical frames: database, mimic, compressor, simulation, general pattern machine. The first 2 are, to use a phrase I learned while working on this piece, they're thought-terminating cliches. They pump the wrong intuitions. The third one, compression, starts to get into more interesting territory, as long as we think in terms of what a compressor has to learn to be good at compressing and dispel with this image of blurry reconstructions. The last 2, simulation, general pattern machine, is where things start to get really interesting. Framing large language models as simulators allows us to ask about what precisely it is they're simulating, what training is most important, and how the simulations are enacted. What kind of prompts can enact what simulations. The idea of a general pattern machine, likewise, is priming us to ask what I think are the right questions about what kinds of patterns are more or less salient and how these compare to human pattern detecting abilities. Thank you.